This is lesson chapter 10.1b. We're doing Lagrange error bound. So as we've seen so far, that the Taylor polynomials provide a good estimate for a function, but it's not perfect. So this is going to cover its accuracy. So how accurate is the Lagrange error bound? So first, we're going to have a definition so we can talk about this. The remainder in a Taylor polynomial, what does that mean? So you have an nth order Taylor polynomial. We're going to define the remainder of this polynomial to be basically the error. When you see r sub n, that is the error, because f of x is the actual value of the function. Pn of x is the Taylor polynomial. So when you take the actual minus the Taylor polynomial, we're defining that as the remainder. So the remainder is another word for the error. Now we have a theorem here, Taylor's polynomial, also the remainder theorem. So we have a function f, we have n plus 1 derivatives, and so we're defining the value of f to be the Taylor polynomial plus the remainder, which is the error. So you can see if you add the Taylor polynomial to the remainder or error, it's f. So it's just a rearrangement of this definition. So f of x is being defined as the Taylor approximation plus the error. And here's what Taylor's theorem says. You can actually find this error. Well, I'm not going to say you can find it. It exists. And that error is that for some c between x and a. So we need to define these things. What is going on? This should look very familiar. That is one of the terms in a Taylor polynomial. In fact, in a Taylor polynomial, it goes up to the nth degree. So what's this? That's the n plus 1 term, n plus 1 term, n plus 1 term. So basically, this theorem is saying the error is going to be the next term of the Taylor polynomial. Just like when we did the alternating series and we had an error bound, we decided that the bound for the error, the maximum error for an alternating series whose terms are decreasing in magnitude to 0, is the absolute value of the next term. Well, Taylor's theorem says something very similar. This time we don't have an alternating series, and now we want to find the error, r sub n, or the remainder, and they're saying it is the next term, but this is different in a Taylor polynomial. It's not exactly the next term. It's the next term for some c between x and a. So what is x and what is a? Well, a, if you remember, is the center of our Taylor polynomial. The center, you could think of that as the point of tangency. Now, I know it's not technically a tangent unless you have a linear approximation, but conceptually you can think of that's the point we start at and that's the point we build our polynomial. So you can think of it as a starting point, and the value at the point of tangency is exact because we define it that way. Okay, what is x? So x is this x. So if you want, for example, if you're trying to approximate f at 0.3, well, x is now 0.3. So x is whatever value you're trying to evaluate your function at. So it's going to depend upon what you're asking for, what actual value. So if this were, I'll make up some values here for you. Say this was 2, and that's a 2, and that's a 2. So the error at 2, for f at 2, that would mean your x here is 2. Now your center is still a, whatever that happens to be for the problem. So the Taylor theorem is saying the error for a Taylor polynomial will be the next unused term in the series. So this Taylor polynomial goes up to the nth degree. So the next term is that, but here's the deal. The derivative is going to be evaluated all values of c between x and a. So there, you don't know what point it's at. It could be any of the values between those two. So the Taylor theorem just says the error exists, but you're not sure what it is. Okay? So that ties into the Lagrange error-bound theorem 10.2. Now, if you look at this, that's just the next term in a Taylor polynomial. Now look at m. M is defined as the n plus 1th derivative. So this is the error again. R sub n is the remainder, which is the actual value minus the Taylor polynomial. And the absolute error, we put the absolute value, is less than or equal to. Now we, on the previous theorem, says equal to. In fact, it's equal to this for some c between your center and x. But we don't know what the c is. So we define it differently. Here's what we do. Since we don't know what c gives you the exact error, here's what we do. We say for some c between a and x, including the endpoints, that's what inclusive means, you're going to pick some number that is guaranteed to be bigger than all values of the n plus 1th derivative for all c's between a and x, including a and x. So if you pick some number that's guaranteed to be bigger, then you're guaranteed your error will be smaller than that biggest derivative in a sense, inserted into the n plus 1th term of the Taylor polynomial. So I wrote it in this form. I think this form is easiest to see. What is this saying? So if you look at this, that is a term of the Taylor polynomial. In fact, it's the next term if we have an nth order. So we're doing the same thing. The error is going to be bounded by the next term, just like we did in alternating series. But here's the difference, and here's the terminology, and here's how you can write it. You want the maximum value of the n plus 1th derivative for some c. Oh, I messed up. This is a c, not an x. Oopsie. So for all c's between a and x. Now here's the problem. The way I wrote this could actually also be x here and a here, depending on which one's bigger and smaller. So your a and x could be on either side, and that's a c again. Sorry about that. I messed up on these notes. I'll have to fix that. So let me fix it here. Bam. Fixed like new. And like I said, this could be this instead, because you don't know what a and x are. X could be smaller than a, therefore you might have to have this. We'll do a few examples of this. It seems kind of confusing, but let's simplify this in our mind. So we want to get a error bound, a bound for the amount of error for a Taylor polynomial. So we're trying to find a bound for the remainder, and that's another definition of the remainder. And again, you could just say error. Now we know it's going to be less than or equal to. Now what's happening, the maximum value that the next term in the Taylor polynomial could be. And it's the maximum value for all points between the center and the value of the function where it's being approximated. So that's a pretty much the summary of it. So we're going to do example after example after example, 3 examples to get through this. So you want to find an error bound, key things, a third order, Taylor polynomial, okay, cosine of 1 centered at 0. So let's define some things. This is telling us our center A is 0. This is telling us our x is 1. And so let me make some connections here. This x is, whoa, that wasn't supposed to be a curvy line. Let's try again. That x is that x. And this center here is the 0. So those are some connections we have to make. Now, we have a third order, so let's go ahead and do this. The error, I'll write this a few ways, and that's not a right way. We're doing it at 1, and we have a third order, so I need to fix this up. This is a 3, which is the actual function at 1 minus our Taylor polynomial at 1. I'm going to write it another way. We could say just error. That's allowed to be said. And that's going to be less than or equal to, and I'm out of room, so that's ugly. I'm going to write it as this. The maximum value for any c between 0 and 1 inclusive, you have to include those, of what? Of the fourth derivative at some c. And then our x minus a, absolute value of x minus 0 to the n plus 1 power, which is going to be 4, because remember, our original is third order. So it's the next term, which is the fourth power, and that's all over 4 factorial. So we need to find the fourth derivative for cosine of x. Our original function is cos, so the derivative will be minus sine x. The derivative of that would be minus cos x, and the derivative of that would be sine x, and the derivative of that would be back to cos x. I believe that's right. Let me double check. Cos, opposite sine. Derivative of sine is cosine, but there's a negative in front. Derivative of cosine is minus sine, and a minus and the minus make a plus sign. Derivative of sine is cosine. So let's write this, which equals, we want the maximum value for c between 0 and 1 of the absolute value of cos x times, now, what's our x? We already determined our x. Our x is 1. So this is going to be 1 to the fourth power, all over 4 factorial. Now, how are we going to do this? So what this is saying, we want a value here, replace this with a value where that's bigger than any of these, because we want to make a bound. And so we want this to be the smallest we can make it, but it's going to be the biggest value that this can be, the maximum value of cos of x. Now this one you could actually do in your head, because you know that cosine is between -1 and 1. So the maximum value the cosine could be is 1. So we're going to say which is less than or equal to, and replace that with a 1. And we have a 1 to the fourth still, over 4 factorial, which is 1 over 4 factorial. Is that 24? I believe it's 24. So in summary, the remainder will be less than or equal to 1 over 24. There's a boundary, because if you look at this chain, this is going to be bigger than this, which is bigger than this, which is bigger than that. So in other words, that's bigger than that. So the remainder must be less than 1 over 24. So that's how you do the error bound. Now you might say, what if this wasn't a 0? Because we know cosine of 0 is 1. So that's going to be the maximum value of that. But what if we went from 1/2 to 1? I don't know the cosine of 1/2. I can't figure out the maximum of that. Well, simply, you could still put a 1 because 1 is bigger than that. So you're safe. Now, if you can find the maximum value, put it there. But if you can't, put a number that's bigger than that value and you're safe. So that's the technique we're going to be using a lot. So that is example 1. Let's go to example 2. Now our function, we can see f of x is going to be e to the x because we're approximating e to the 0.45. Now, what's this 0.45 tell us? That's our x. X is 0.45. That's the x we're using, and that's going to be that. And they tell us a is 0, so that's going to be 0 again. So we want the Lagrange error bound. We can say the remainder for a, what degree is this? 6th degree at 0.45, which I can say is the error. And that's going to be less than or equal to. And here's the wording again. It's going to be the maximum value. Now it's going to go from 0, c will be from 0 to 0.45. And then I want the 7th derivative. The 7th derivative for some c, absolute value, because it's absolute error, times our x is 0.45. So when x will be 0.45 minus 0 to the 7th power all over 7 factorial, which is less than or equal to the 7th derivative. Actually, let's do an equals here because we're just going to find the 7th derivative, which is equal to this e to the x. I am my own grandpa. That's going to happen over and over. So we still have c between 0 and 0.45. Our 7th derivative is e to the x, but it's e to the c because we're evaluating for all c's between those 2 points. This will be 0.45 to the 7th all over 7 factorial. Now, here is where we run into some problems. We're trying to evaluate e to the x. Yeah, how do we do that? I don't know. So we're approximating it using the Taylor polynomial, and now we're finding the error with that Taylor polynomial. Since we really don't know what e is, or e to the x is, because if we knew that, we wouldn't need a Taylor polynomial, we cannot figure out e to the 0.45. Now the e function looks like this. So the farther right you are, the bigger it is. So at 0.45, that's going to be the biggest value, right? So technically it's e to the 0.45, but that's what we're trying to find. So I can't use that for my error bound. So I have to use some logic. Let's see, this is going to be less than or equal to e to the 0.45. And then we still have 0.45. I've made this, I'm going to just move this whole thing down because I can. Why? Because I can. Whoops. That wasn't supposed to come with us. Let me put those back up there. 0.45 to the 7th over 7 factorial. Now, we're going to pick a number that we can deal with. So I think you'll agree with me that we can say e to the 0.5. And you're going to say, why'd you put 4.5, Yoshida? Because that's a square root. Okay? So I'm doing more steps than you would actually write. I just want to make it very clear. Now, we could figure that out by hand. I don't want to do that, so I'm just going to leave it like that. But that's doable. That we can't do. So here is the logic. I say that's less than square root of 4. What? Why 4? Because I know how to take the square root of 4, and 4 is bigger than e. So that's a doable number in my head. So here's my error bound, 2 times 0.45 to the 7th over 7 factorial. So I have found an error bound for that. I know it's kind of weird. Part of it is because you don't actually have the right answer, meaning there are multiple ways you can do this. So it's kind of bothersome that we do this weird thing where we do, oh, instead of 0.45, let's do 0.5. And instead of e, let's do 4. But we're doing all of this so we can find a nice number 2. And to summarize all this is less than that. So this is a boundary for our error. So all of that, yeah, just to say we have a boundary. Now, it's not a perfect boundary because we have a range of what the error can be, but it just becomes a nice boundary for us to work with. So that's why we did that. Okay, so I guess I should have a final summary. The error is less than 2 times 0.45 to the 7th over 7 factorial. In fact, if you want to make this even prettier and easier, you don't have to, but we could do this. This is crazy. You might think it's crazy. 2 1/2 to the 7th over 7 factorial. That's easier to calculate than 0.45 to the 7th, and 1/2 is bigger, so I shouldn't put it equals there. Sorry. I should put a less than. So I'm just continuing to go through this boundary state. So that's going to be the top. You're going to see that one of these is going to cancel with one of those. So that's 1 over 2 to the 6th. So 1 over 2 to the 6th power, 7 factorial. 2 to the 6th, what is that? 4, 8, 16, 30, 64? 64 times 7 factorial. We're just trying to make our life easier. Do I want to multiply that? I don't want to multiply that. So I'm going to do this. 1 over 64 times 7 factorial. Now, we could have actually stopped there. We didn't need this. I'm just trying to make it prettier. But this original one is fine also. I'm just showing you there's multiple possibilities for what we're doing here. Oh, that's an inequality. What you doing, Lamo? Yeah, it's inequality, not equals. So basically, I just took that on the left, that on the right, because that's a true statement. All right, so that's why I think Lagrange bothers people, because we kind of don't have a answer. Or we don't have the answer. We just have a answer that works. We'll do one more example. This is it. So we have an nth order Taylor polynomial. This one's kind of weird. So they're telling you what it looks like. That Taylor polynomial looks like that. And we want to find the bound of the error for a third order Taylor polynomial. But here's where it's weird. Our x can be any number from -1/2 to 1/2. That's kind of weird. And so it's going to be a little more difficult finding the error bound, but we can do it. So the error for a third degree Taylor polynomial for any number, okay, that's where it's weird, is between -1/2 and 1/2. And using the Lagrange error bound, that's less than or equal to the maximum value of the fourth derivative at some point C. Now, here is where we get a little sketchy here. The center's at A, right? So here's where your brain needs to think. The center's at 0. If we can pick any x between here and here, so technically it could be 0 all the way to 1/2, right? Or it could be -1/2 all the way to 0. So if you happen to pick the -1/2, here it would be your range for domain for C. And if you pick 1/2, it would be from that. So if you combine these two, you see that C could be anywhere from -1/2 to 1/2. That's weird. That's weird. So C can be anywhere from -1/2 to 1/2. And then you're going to do x minus 0, and that's going to be raised to the fourth power, and that's all over 4 factorial. So picking our C was very strange. And let me do that one more time for you. So if you chose your x to be 1/2, you would find your C would have to be between 1/2 and your center A. I should have probably done this. A is 0 because that's where your center is. Your x, and that's what we're dealing with here, your x could be anything from -1/2 all the way to 1/2. So if you choose the farthest right boundary, 1/2, that puts your C, wow, my writing is horrible. That's a half between 1/2 and A, but A is 0. So I'm going to put a 0 there. Now, if you choose your x to be -1/2, then it's going to be from -1/2 all the way to your center A, which is 0. So because C can be any number from -1/2 to 1/2, we have all of this must be true. So C is now between -1/2 and 1/2, and that's why it shows those values. And then we have more stuff to do. So let me write this down again. Oh, those are equals, by the way. Now the fourth derivative, we're going to find that, so let me leave that like that. Then we have x to the fourth, which is always positive, so I don't need my absolute value, over 4 factorial. But here's my claim. We're trying to find the maximum. So what x gives us a maximum value? Well, if x is between -1/2 and 1/2, the biggest it's going to be is when x is 1/2. So I choose 1/2 for that x. That's the biggest value we're going to get. But I need to find the fourth derivative. So our function is ln 1 minus x. The first derivative is going to be 1 over box times derivative of the box, which is -1. So I get this. Well, the second derivative, I bring the -1 in front, box, I subtract 1 from the exponent, but then I need to multiply by the derivative of box, which is going to get me something, a negative, because I have 3 negatives, I guess. And it's going to be 1 minus x to the negative 2. Then the third derivative, there's a negative here, so I just copy that. And then I bring the negative 2 in front, 1 minus x, I subtract 1 from the exponent times the derivative box again. And I have 3 negatives, so it's all negative, 1 minus x to negative 3. And then the fourth derivative, I bring the negative 3 in front, 1 minus x, I subtract 1 from the exponent times the derivative box, so it's negative 1, or negative, whoa, Yoshida, there's a 2 there. So there's a 2 there, negative 6, 1 minus x to negative 4. All right, let's place all of this. I guess we'll just go vertical here. This will be negative 6, 1 minus x to the negative 4. You know what? Let's make it a fraction. The negative power moves to the bottom. So it's negative 6 over 1 minus x to the 4th power, which is less than or equal to. So we need the maximum value of all of that. All right, how are we going to do this? What value of x here, I'll do a different color. What value of x, or c, that's a c. That's a c, you see? Why am I messing up? I'm doing that on purpose so you don't make that mistake. Yeah, right. When is a fraction the biggest? When the denominator is the smallest. When is 1 minus c the smallest? I claim it's smallest when you have a 1/2 because you're subtracting the most. So that's less than or equal to negative 6 over 1 minus 1/2 to the 4th, and another 1/2 to the 4th over 4 factorial, which equals 6 over 1/2 to the 4th times 1, whoa, I don't know how that changed to a 4. 1/2 to the 4th over 4 factorial. What's nice, those cancel, which equals 6 over 4 factorial, which is 6 over 24, I believe, which is 1/4. So, this is crazy. Actually, this shouldn't be x. Yeah, it is x. For any x between negative 1/2 and 1/2, we're going to get less than or equal to 1/4. So that's going to be our error bound for part A. Crazy, huh? Hopefully that all makes sense. Part B, how many terms of Taylor polynomial are needed to approximate the value? So I'm going to erase all of this work here. Maybe I'm not going to erase the derivatives. I might need that. So let me erase all this. How many terms are needed to approximate the values with an error less than 10 to the negative 3 on the interval? So, wow, this is going to be a little bit different. Oh, maybe I shouldn't have erased that. Let me think about this. Let me process through this. I think we're okay. Here's where we're going to get weird. Look at these derivatives, and we're going to have to play with this. This is going to be negative 1 over 1 minus x. Negative 1 over 1 minus x squared. Negative 2 over 1 minus x cubed. Negative 6 over 1 minus x to the 4th. Now we look at a pattern. That's going to be 1, 1, negative 2, negative 6. Let's look at what the 6th derivative is going to get, or the 5th derivative is going to get us. So we have a negative 6, and then that negative 4 needs to come in front. So it's negative 4 box, subtract 1, that's going to be negative 5, and derivative of box is negative 1. And look what we have now. It's going to be 24, negative 24, 1 minus x to negative 5. Now, if you look at these, those are factorials. Because what we're doing, we're multiplying negative 2 times that 3. And we get 6. Then we take that and multiply by 4. Now we're going to take that and multiply by 5. So if you look at this pattern, the nth derivative is going to be, okay, let's get this down. I didn't write this last one down. Negative 24 over 1 minus x to the 4th. So seeing that pattern, that's going to be negative 4 factorial over 1 minus x to the 4th. That's the 4th power. And this is negative 3 factorial over 1... Whoa, I messed up somewhere. This is a 5th. Is that right? Let me... Yeah, that looks right. I believe that looks right. And then this is going to be 1 minus x to the 4th, negative 2 factorial over 1 minus x to the 3rd, negative 1 factorial, 1 minus x squared. If this follows this pattern, it's negative 0 factorial over 1 minus x to the first power. So in general, if you look at this, this is going to be n factorial. Let me double check this if I'm doing this right. It might be n plus 1 over n plus 2. Do I have this in the right order? I think I do. So we're getting the derivative is going to be n plus 1 factorial negative over 1 minus x to the n plus 2, which is kind of weird, but for the Lagrange error bound, we need the n plus 1 derivative. So we place, that's going to change everything. That's going to make this n factorial, negative n factorial, over 1 minus x to the nth plus 1 power. All right. So my brain is on overdrive here. For some reason that doesn't look right to me, but I'm okay. So let's think about this. If we want the 5th, n would be 4. Yeah, that's right. For the 5, we do 1 less here. That's 1 less, and that's the same. So the 5th derivative, that's 5, and that's 1 less, so that's 1 less than that. So we're good. We're good. We're good. We're good. I think that previous one was weird. Yeah, that should be n minus 1. I see why I'm confused. Sorry, guys. That should have been an n minus 1. Because if you have a 5th, you want a 4th, that's 1 less, and that should just be n. Now it all makes sense. And then I replace all the n's with n plus 1. I get that. Okay. That's all to say our error now. We're doing, I don't know why that keyboard's there. I'm not going to be able to get rid of that. It's going to drive me nuts. I'm just going to throw it over here. Okay, so our error, we want it less than 10 to the negative 3. So what is the error? The error, absolute value of the error for some x, and that x, again, is between negative 1/2 and 1/2. That's how we're defining the x, is less than or equal to the max from negative 1/2 to 1/2 of the absolute value of the n plus 1, so that's going to be negative n factorial over 1 minus x to the n plus 1 times x minus, well, our x we decided is maximum at 1/2 minus 0 to the n plus 1 power all over n plus 1 factorial. What is going on? Let's simplify this. Okay, we determined the best x here to get the maximum value is 1/2. So we have less than or equal to, and this is going to be n factorial, the negative disappears because the absolute value, over 1/2 to the n plus 1 times 1/2 to the n plus 1 all over n plus 1 factorial. Those will cancel. That cancels with that, leaving n plus 1. So this equals 1 over n plus 1. But the whole problem is asking the error to be less than 1/1000th. So that's going to be less than 1/1000th. Let's flip both sides. N plus 1, flip the inequality. So n must be greater than 999. So that is a crazy problem. These are much harder. That is harder than any AP question you'll get. But hopefully you understand the concept of Lagrange error bound.